Hi, my name is Stephen Agee, and this is my CSCI 403 semester project, Vibration Predictions for Hydropower Generators. It's just kind of an overview of the project to give some motivation. Hydropower generators are typically large, and as a result, they experience high vibration. Failure to recognize high vibration can lead to catastrophic failures. The long-term goal is to reduce operation and maintenance costs with predictive maintenance. This is based on data science using visualization, trends, and machine learning to predict maintenance activities instead of doing them at an incremental rate. The data acquisition for this project, it used Hydropower machine condition monitoring data, which was acquired from one unit to perform analysis. And there were two objectives in this study. The first objective was to predict rough zone, which is damaging vibration, based on various features. The features selected included rough zone, which is our target variable, power output, net head, and gate position. About 7,500 samples were selected per feature, which represents about 3 months of generator operation, and that's downsampled data. The second objective was to determine factors contributing to high vibration during synchronous condense. And these features included turbine guide bearing vibration, lower guide bearing vibration, rough zone, power output, reactive power output, gate position, and air gap readings. So synchronous condense mode is a mode where the water is cleared out of the draft tube of the generator, and air is actually injected to create kind of a bubble. So the turbine is spinning in air. It's often called spinning reserve, and it gives the opportunity to provide grid stability while not generating electricity. And for this analysis, about 4,200 samples were selected per feature, which represents about 1 day of generator operation. So the first objective was to predict rough zone. So here's an initial visualization showing a rough zone map for a data set. So rough zone maps are typically used to determine safe operating ranges for the generator. So you can see we have net head on the y-axis, power output on the x-axis, and rough zone RMS as each point's shading. So as you can see, net head does have an effect on power output. As net head goes up, the data point where rough zone RMS starts to become more extreme also goes up, so they are related. But what if net head goes outside certain measured ranges? So what if the reservoir level drops below what we've seen before? What if it rises before what we've seen before? So we wanted to predict the rough zone outside of the acquired data for net head. So in order to do this, we use linear regression, which was used to predict rough zone based on various features. Coefficient of determination, or R-squared value, was calculated for each combination of the features. And the highest accuracy that was achieved was with power output, head, gate position, and that was using 7 polynomial features. So in addition to those 3 features, for each feature, polynomial features were also generated. And so there's a little table just showing the accuracy for each as each feature was included. So here's just a plot showing the rough zone map, predicted versus actual. So as you can see, it looks pretty similar, and you can see that relationship as net head goes up, the rough zone tends toward a higher power output. So you can see that slight positive slope there. And another thing to note, these plots were generated for gate position and power output. The second objective was to analyze the high vibration, as I mentioned before, during synchronous condense. So we were noticing high turbine guide bearing displacement when in synchronous condenser mode. In other words, when the gate position is 0. So what are the contributing features? That's the question we're trying to answer. You can see there's some plots, gate position over 1 day. You can see we used 1 day's worth of data, and the gate position was 0%. And you can see we also had the turbine guide bearing displacement increasing over that time range, and lower guide bearing displacement was kind of random. So we used regression analysis, and we used all those features that I mentioned before, and the only correlation was with rough zone, which is actually derived from turbine guide bearing and lower guide bearing displacement, so that wasn't really useful information. We also did principal component analysis to find the 4 features with the highest explained variance, but the results really didn't show much separation of the data. You can see there we have turbine guide bearing displacement as the plot shading, and then the principal components on the axes. So for future work, we really want to validate those rough zone predictions with cross-validation testing, and also use data from other generators. And then another thing that needs to be done is to figure out why we're getting high vibration and synchronous condense, because that is still unknown. And we want to maybe compare with the healthy unit and see how the data stacks up. Thanks for watching.